Hi, I'm Selva Prabhakaran. In this one, let's understand the binomial distribution very, very clearly. We will understand with a simple, clear example so that you will not forget what we are discussing in this particular video. Now, to understand this, we will assume that you are a owner of a retail store and you have stocked two particular brands of shampoos. So, brand A and brand B. You have these two brands. What we want to know is whether the incoming customers, do they have a preference specifically towards more preference for any one of these brands, right? So, let's imagine there are 5 customers coming in. Amongst these 5 customers, either one of these cases are possible, right? So, case 1 is all the 5 customers are buying brand A. Case 2 is 4 of them are buying brand A and one customer is going for brand B. The remaining 2 cases is like the opposites. 3 of them are going for brand A and the 4th case is 3 of them are going for brand B. Now, you would expect that suppose if both of these brands don't have any specific preference for the customers, right? The customers are not having any specific liking for the brands. You would expect that these 2 cases, the 3rd case and the 4th case, these 2 cases to occur more frequently, to simply put. It is not to say, however, that if the customers don't really have any preference for A or B, if that is the case, then these cases will never happen. It is very much possible that scenario 1 or 2 can also happen if customers really don't have a preference for any of these 2 brands. So this is where binomial distribution comes in. It helps to understand what to expect when customers really don't have a preference for A or B. What should we expect? Also, to put it in general form, right? What to expect when customers have a certain probability of preference towards one of these brands. Suppose customers prefer brand A 70%, right? 70% more likely to prefer brand A. If that is the case, what should you expect? How should you expect the customers to behave? Now let's tackle this. Let's take one particular case where just one customer is going for brand A and 4 customers are going for brand B. Okay, suppose this situation has happened. What is the probability that this could occur when people did not really have any preference for either of these brands? Hope the question is clear. Now, to understand this, binomial distribution gives us a probability mass function, like how we have probability density function for normal distribution. We have probability mass function for all discrete distributions. Binomial distribution is one of our discrete distribution. Now, it is defined as the probability of getting K successes out of N trials. So in our previous case, we had 1 customer visiting A and 4 customers visiting B. So in this case, we will call a customer visiting the brand or buying brand A shampoo to be a success. Buying brand A is equal to success. Now, given this scenario, can you come up with the values of K, N and P? Now we are going to assume that there is no particular preference between any of these brands. Customers are likely to purchase A or likely to purchase B also with equal preference, right? If that is the case, then the probability of success is going to be 0.5. Equal probability. This is nothing but probability of a customer buying brand A. This is what success is in our case. And that value is we are assuming to be 0.5. Okay, so that is P here. K is the number of successes. So in this scenario, the number of successes is 1. Right? So K value is going to be equal to 1. And the number of trials is the total number of trials. So we have 1A and 4Bs, right? So 1 plus 4 equal to 5. That is the total number of trials. Now for this to happen, amongst 5 trials, we getting 1 success out of 4 trials, assuming there is equal probability, 0.5 probability. That is nothing but NCK, N combination K. So this would be 5 combination 1 multiplied by, what is P? Probability of success is 0.5 raised to the power of K equal to 1. Again multiplied by 1 minus P is also 0.5. Right? This is failure. So this is people buying A. This is people buying B. And this is people buying A. Left hand side is people buying A. Okay. So 0.5 power 1 and 0.5 power 4. This turns out to 5 multiplied by 0.5, the whole power 5. Okay, so this is the answer. This is the whole answer to the problem that we are dealing with. How would you approach this if we did not have this formula? So let's solve it without the formula. Okay, so if no preference, then probability of success is going to be equal to 0.5. So we know this, we have established this. So we want 1A and 4Bs. 1A and 4Bs. This could happen in any or all of these combinations. Okay, the A could occur in the first trial, and remaining buys are from B. Likewise, this could also happen. This is also 4Bs and 1A, any of these situations. Okay, now let's understand the probability of the first customer to buy A is going to be equal to 0.5. Alright. Similarly, the probability of the second customer going to buy bottle B, shampoo B, is again going to be equal to 0.5. Same is the case for all the 3 cases or the remaining 3 cases. And all of these 5 events are independent of each other. So we multiply all of these probabilities, 0.5 and 0.5, 0.5, 0.5, 0.5. Okay, you multiply this basically works out to 0.5 power 5, which is nothing but this particular value. And if we want to calculate the probability of this event occurring, this sequence occurring, then the formula remains the same, because this probability is also 0.5, probability of picking A is also 0.5. So 0.5 power 5 is the same for all of the cases we have here. So finally, the probability of getting 1A and 4B is nothing but 5 times the probability that we computed. This turns out to be 0.15625. So we can also write this as probability of success given there is no preference. This also means that probability of success equal to 0.5 in our case. Okay, so this works out to this particular value, which is exactly the same as what we had computed using this formula that we had seen earlier. Now, having a formula for this makes it a lot more convenient, because now you can compute what is the probability of, say, 2 successes given there is no preference. No preference again is 0.5 only. If this is what we want to compute, we can directly apply it into the formula. So 5C2. So 5 is the number of trials n. CK is k equal to 2. 2 successes, and probability of success is 0.5. That does not change. Okay, 0.5 power 2 and 1 minus p. This is also 0.5, that power 3. Okay, that works out to this particular value. Actually, we can plot the whole thing where n equal to 5, the number of trials is equal to 5, and k equal to 0, 1, 2, 3, 4, 5 for all possible values of k. We can compute the PMF. The y-axis here is the PMF, right? We can compute this and plot it like this. This will not be a continuous normal curve like what we get with normal distribution, right? Since this is binomial distribution, which is discrete in nature, we will have dots, or you can have bars also in this case. You can have these bars for each of the discrete values of k for the various range of values from n equal to 0 to 5. Now, how about a generalized version for this? Now, what is the probability of getting exactly 2 customers buying brand A, right, out of total of 5 customers, when 75% of the customers truly prefer shampoo A? So what this essentially tells us is, when P, the probability of success is going to be equal to 0.75, what is the probability? What is the probability that people will buy 2 shampoos from brand A, 2 out of 5 trials, given that the probability of success is going to be equal to 0.075, right? 75%, 0.75. Can you try and compute this? And while you are at it, can you also compute the probability of getting 4 customers to buy brand A, 4 customers to buy brand A out of 5 customers, when the same probability, 75% of customers truly preferred shampoo A? Pause the video right now and try it out if you have a computer nearby. And once you compute the probabilities, write in chat which of these 2 situations, that is k equal to 4 and or k equal to 2, which of these 2 situations is more likely to occur when p equals to the probability of success equals to 0.75. Consider to pause this and try it out. Meanwhile, let me show you the answer. So here it is. The probability of getting 2 successes out of 5 trials and p equal to 0.75. So that is 5C2, 0.75 power 2 multiplied by 0.25, which is the failure, 1 minus p, right? Probability of failure, power 3. That works out to be this particular value, 0.08789. Likewise, you can compute it for k equal to 4 as well. So 5C4, and you substitute all the remaining values, you get the probability to be 0.3955. So comparing these 2 values, we see that the chance of getting 4 successes is greater than the chance of getting, the probability of getting 2 successes when p equals to 0.75. So congratulations if we got it right. In the next one, we will solve a completely different problem based on this whole idea of binomial distribution. Then we will proceed to the part 2 of binomial distribution, where we will deal with certain theoretical aspects of how to work and understand binomial distribution.